Hey y'all, welcome back. On tonight's homework, we're focusing on position, velocity, and acceleration and their relationship to each other. Specifically, that the derivative of position is velocity, and the derivative of velocity is acceleration. So we'll keep that in mind as we answer all these questions. Not all these questions are going to have to do with position, velocity, and acceleration. Hopefully, you've noticed by now that I like to give you questions from previous lessons kind of mixed in there, just so we get a little taste of everything, and so we don't forget how to work some of the problems we did at the beginning of the unit. So they won't all be about those, but we're going to throw those in there as well on tonight's homework. So number one says the table below gives the value of f and its derivative at several values of x. If g of x, which is the reciprocal of f of x, what is the value of g prime 3? Be sure to show what g prime x is before you find g prime 3. So first, I want to throw this out there because I've seen this students struggle with this before, is when we try to find the derivative of this, when we were finding the derivative of algebraic functions and we had something like 1 over x squared, we saw that it was convenient to write this as x to the negative second power and find the derivative of that using the power rule. And that's still going to be our go-to strategy when we have an algebraic function like that. But when we have a generic function like this, we want to be careful about trying to differentiate this as though it was f of x to the negative first power, which it is. But this is actually a composite function. We have a function kind of plugged inside of another function. And we haven't yet gone over exactly how those derivatives are going to work. We need something called the chain rule to handle that. And so for now, you can still use that power rule if you have x squared or like a polynomial term. But not if you have some generic, or really if you have any function that's not a monomial term in the denominator like that. So, okay, let's go ahead and find this derivative a little different way. We're going to use the quotient rule. So that's going to be the derivative of the top, which is going to be 0, times the derivative, not the derivative, but just the denominator, f of x, minus the top, which is 1, times the derivative of the bottom, which is just f prime x, all over f of x squared. Now, it is acceptable notation to put that 2 here, but just for the sake of clarity in my argument here, I'm gonna write it like this. It's a little bit more blocky, but I think it'll be more obvious that I'm squaring this f of x rather than taking the second derivative of it. So now I'm trying to find g prime 3. So I'm trying to evaluate this when x is 3. Before I plug in 3 here, I'm going to simplify this a little bit. 0 times f of x is just going to be 0, and 1 times the derivative of f is just, well, the derivative of f. So we have the opposite, or negative, derivative of f over f of x squared. So now I am going to go ahead and plug in 3. So the opposite of the derivative of f of x f of 3 divided by f of 3 squared. So to evaluate these functions, and both f and f prime, we're going to use the table. And we see x is 3 right here. So if I need to find f prime 3, I'm going to look at the values for the derivative of f in this row, match it with the column 3, and report back 3. So negative 3 over f of 3. So I'm still looking at this x, but now I'm focused in on f of 3. So f of 3 is negative 9, and that number is squared. So we have negative 3 over 81, and you can just leave it like that. This does reduce a little further, you divide both of those by 3, you get negative 1 over 27. So I'll box that, but you're actually good to box this answer, and actually you're even good to box this answer here too. On those free response items, you do not need to reduce or simplify or anything like that. Okay, let's take a look at number 2. The functions f and g are piecewise linear functions whose graphs are shown below. Use the graph to answer the questions that follow. So it's saying h is the product of f and g, so you can tell right away I'm going to have to use the product rule here. Determine each of the following. Yep, here we go. The derivative of h. So we're going to differentiate this using the product rule, almost in the pretty much in the abstract form that we write it for as our template here. So f prime g plus f times g prime. Yeah, all right, there we go. And then we want to evaluate that when x is 3. So this is going to be f prime at 3 times g at 3 plus f at 3 times g prime at 3. And we're going to use the graph to evaluate each of these. So let's look at function f first. So this is talking about the slope when x is 3. This is talking about the value of the function when x is 3. So let's look and see what's happening at 3, which is right here. We're zeroing in on this point right here, because this is, let me go ahead and highlight this, make it a little bit more clearer. Here's f of x right there. So the value of the function, the value of f at 3 is going to be 1. So that's f of 3. And the slope, well, let's figure out what the slope is. It looks like if I pick these 2 points, going down 1 over 3, so the slope is negative 1/3. Now let's take a look at function g. So I'll erase all this. Function g is highlighted here. And we want to evaluate both the y value of function g and the slope at x equals 3. So here's 3. We're looking at g here. The y value here is 3. So it's going to be negative 1/3 times 3 plus 1 times the slope, which we can see is up 1 over 1. So that's just going to be 1. So negative 1/3 times 3 is going to be negative 1. Plus 1 times 1 is 1. Yeah, this just equals 0. Number 3 says if p is g divided by f, determine each of the following. So we're going to use the quotient rule here, kind of like we did in number 1. So it's the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Again, I'm going to write this with brackets. So now we want to evaluate this when x is 3. So this is going to be g prime of 3. And luckily we've already evaluated a lot of these. So you can just look back at our work at the previous h prime of 3 problem to get the values we're going to need here. All right, I'm going to run out of room here, aren't I? So g prime 3, just going to highlight where we already calculated that, was 1. F of 3 was also 1. Real nice numbers here. G of 3 was 3. And f prime of 3 is negative 1/3. F of 3, we can just get that again, was just 1. It's going to be a really nice denominator there. So yeah, we can go ahead and evaluate this. 1 times 1 is going to be 1. We've got negative 3 times negative 1/3 is going to be positive 1 over 1. So this is going to equal 2. So the slope of this function p when x is 3 is 2. The instantaneous rate of change of function p at x equals 3 is 2. There's a lot of different ways that we can describe what's going on here. Number 4 says determine the derivatives for each of the following functions. And yeah, I just don't care how simplified these are. I want you to get in the habit on the free response of just not simplifying anything. Okay, you don't need to reduce any fractions. You don't need to simplify any expressions. Once you have your answer, go ahead and box it and save yourself time and potential errors. So for A, we want to find the derivative of this function. So we're going to just take each term here and differentiate separately. Maybe before I do, I'll rewrite these first two terms. So I'll rewrite this one as x to the 3/5, and this one as x to the negative second. And I'm doing that so that I can more clearly see what's going to happen with the power rule. So now let's go ahead and use that power rule on these first two terms. 3/5 x to the power of negative 2/5 minus, we're going to have to bring down that negative 2. So minus 2 times x to the negative third. And then the derivative of cosine is the opposite of sine. B is e to the x divided by x cubed plus 2. So we're going to need to use the quotient rule. Derivative of the top is just e to the x. Nothing happens with that one. Times x cubed plus 2, the bottom, minus the top, e to the x, times the derivative of the bottom, which is 3x squared, all divided by x cubed plus 2 squared. And you can just go ahead and leave it like that. This is really just a question of, do you understand what the quotient rule is, and do you know how to do some of these transcendental derivatives? The next one, we're going to have to use the product rule. And so here's our function 1, here's our function 2. We've got an algebraic and a transcendental, specifically a trigonometric function here, tangent. So we're going to need to know what that derivative is. We'll come back to that. But let's first get this product rule started. So the derivative of the first is going to be 16x times the second. So 16x times tangent x plus the first one, 8x squared, times the derivative of tangent. So I'm going to go ahead and just give it to you. It's secant squared. And if you've got that memorized, that's great. But if you have trouble remembering what the derivative of tangent is, don't forget that you can rewrite tangent as sine over cosine and just derive the derivative by using the quotient rule on this. So you do still need to know what the derivatives of sine and cosine are, but if you do, you can figure out what the derivative of tangent is without having to memorize it. So just, you have that in the back of your head. So like if you're just like not sure what the derivative is in the middle of a test, or you just can't remember it, know that you can still figure it out on the spot. But it is better to just go ahead and remember it. We're not going to simplify this at all. We're just going to leave it like that. Number 5 says determine the second derivative. Okay, so we're going to differentiate this twice. And at least on this first go through, we're going to, this y prime, we're going to use the product rule with these two being our two expressions, two functions. So the derivative of x squared is going to be 2x times e to the x plus x squared times e to the x. And then we need to go ahead and differentiate that again. So we're going to have to use product rule here and product rule again. So we got a double product rule here. Maybe some terms will be able to be combined at the end, but we don't have to combine the like terms. Let's go ahead and find this next derivative. So the derivative of 2x is 2 times e to the x plus 2x times e to the x. So all that just came from the derivative of this. Yeah, we use the product rule there. And now we'll differentiate the next product. So derivative of the first, 2x times the second, e to the x, plus the first, x squared times the derivative of the second. So we do have some like terms we could potentially combine. We've got two of these 2x e to the x's. So we could combine that into 4x e to the x. But we can't really combine these other two terms with anything. So this is fine to leave it like this. You might see it if it was a multiple choice item. There's a possibility that you would see the answer written like this. But that's really as far as you could get with this one. Number 6 says let H be the product of f and g. So probably going to have to use some product rule here. Determine the equation of the tangent line to H at x equals 1. So for determining the equation of the tangent line, we know what to do here. We've solved a ton of problems like this. I'm going to keep throwing ones like this at you. Go ahead and write down point, slope, and write the point slope form. Let's just get that template ready to go. So to get the point, we're going to use the original function. Okay, so we're going to use like f, or in this case, h. And then to find the slope, we're going to use the derivative of h, because the derivative is the slope. So first, let's find that point at x equals 1. So we know that our x coordinate is going to be 1. And to find the y, we're just going to substitute 1 into the function h. So we're going to find h of 1, which is f of 1 times, not h, g of 1. Well, f of 1 we can find in the table right here. F of x, when x is 1, f of 1 is negative 6. And g of 1 can be found right here. G of x, when x is 1, is 2. So negative 6 times 2 is going to be negative 12. So that's going to be the y coordinate of this point. And that is the point on H that we're trying to find the line that's tangent to. The slope is going to be found by finding the derivative. And so this is where that product rule is going to come into play, because we need to find h prime. So that's going to be f prime times g plus f times g prime. Now, if we want that specifically at x equals 1, we want to substitute in 1 into h prime. Now we can evaluate each of these separately by looking at the table. So f prime of 1, we can see that that's going to be 3. G of 1 is 2. F of 1 is negative 6. Put the parentheses around that so we know it's not minus. Times g prime of 1, which is 8. So we're going to multiply all this together. Oh, wait. No, what am I doing? Where did that plus come from? Yeah, you know what? Let me just fix that up. Let's write that as minus. Okay, yeah, this will be a lot easier to do. 6 minus 32. No, not 32. 48. It's going to be negative 42. Okay, so that's the slope. Now we're ready to write our equation. Y plus 12 equals negative 42 times x minus 1. And that is, finally, we got our equation there. Number 7 says if the second derivative of y is 0 at the point 2 comma 0 on the graph of this, determine the value of b. All right, so let's first find the first derivative of y. That would be 3x squared plus 2ax plus b. And then the second derivative of y would be 6x plus 2a. And it's saying y prime is 0 at the point 2 comma 0. So that's when x is 2. We can use that to find a. And then once we know a, we should be able to find b. So we have 0 equals 12 plus 2a. So negative 12 is equal to 2a. So a is going to be negative 6. So now that we know that a is negative 6, we can plug that in to this equation here. Or no, not that one. We don't want that one. We want the original one. Because we know that 2 comma 0 is a point on that graph. So this has got to be a solution to this equation. So if we plug in 2 for x, 0 for y, and now we've got a, we can use all that to find b. So 0 equals 2 cubed plus negative 6 times 2 squared plus b times 2 minus 8. Again, just to kind of go over what I was plugging in there, the 2's are the x's, all right? And I know that I'm plugging in 2 because I know this point 2 comma 0 is on the is on the curve. I plugged in 0 for y, and I plugged in negative 6 for a. Now that I've got all that written out, we can simplify this equation and try to solve for b. 2 cubed is 8. And then we've got 2 squared is 4 times negative 6 is going to be negative 24 plus 2b minus another 8. So we have the 8 minus 8. Those are going to cancel each other out. We can add 24 to both sides to get 24 equals 2b. So I'm getting b equals 12 here. Number 8. If f of x is e squared, then what's the derivative of f? Okay, this is kind of a question just to make sure you're really paying attention to detail here and that you know what's going on. So this one's kind of funny. E squared is just a constant, right? There's no x here. It's just a number. E is, roughly 2.7. And so e squared would just be roughly 2.7 squared. It's just a number, meaning it's just a constant. It's just a value like 5. Not exactly like 5, but it's a real number in the same sense that 5 is. So the derivative of any constant is 0. I know you've been waiting for a position velocity acceleration question after this lesson, and I'll give you one. This is really not going to be the major focus of our unit. We are going to come back to this idea of position, velocity, and acceleration and the relationships to each other in the future, but I just wanted to give you a little taste of it. So here's one problem that we can solve. The velocity of an object in meters per second is given by this velocity function. It's quadratic. Determine each of the following, including units. So first, what is the initial velocity? Well, that means we want the velocity when time is 0. Okay, the time is 0. That's what, when you see that word initial, that's what that really means. So the velocity at time 0 is just going to be negative 3 times 0 squared minus 5 times 0 plus 7. So this is just going to be 0 plus 0 plus 7 is 7. And the velocity here is going to be in meters per second. We want to make sure to include units in this application question. B says, what is the speed at t equals 2? Now, one thing that, I can't remember if I mentioned it specifically, but speed is the absolute value of velocity. Okay, so it's velocity without the direction. Speed is a scalar, while velocity is a vector. So velocity is going to describe how fast the object's moving, but also give you information about whether or not it's moving to the left or to the right. Speed is just going to have the information about how fast it's moving. So you're always going to be positive. So anyway, at t equals 2, I don't know if that's going to come up here, but if we do get a negative velocity, we're going to have to negate that number. So at t equals 2, we want v of 2. So negative 3 times 2 squared minus 5 times 2 plus 7. Negative 3 times 4 is negative 12. 5 times 2 is 10. And so let's see here. We've got negative 22 plus 7. Or I think it might be easier for me to group negative 10 and 7. So that negative 10 and 7 is going to be negative 3. Negative 3 and negative 12 is going to be negative 15. So negative 15 meters per second. Now, this right here is the velocity when time is 2. Speed is going to be the absolute value of velocity. So in this case, the speed is the absolute value. So the speed is the absolute value of negative 15, which is 15 meters per second. So just a little bit of a nuance there. It's really a vocabulary issue. I'm not going to be totally disheartened if you were to put negative 15 meters per second. I'd still have to take off, some, like maybe a point at the very most, if you were to do something like that. It's not the biggest problem, but I do want you to understand that there is a difference between speed and velocity. Speed is describing a scalar, which is a magnitude without direction, whereas velocity has the magnitude, which is the amount that you're measuring with a direction. So the plus or minus is that extra piece of information. Part C says, what is the acceleration at t equals 3? So to find the acceleration, we're going to have to differentiate the velocity function. So remember that velocity is the derivative of position. Just want to remind you of that. And velocity's derivative is acceleration. And so you really could go from the second derivative of the position graph of function and get acceleration. So this is the relationship. When I say that I want you to understand what position, velocity, acceleration, and the relationship between each other, what I'm talking about is understanding this sort of hierarchy of derivatives that relates these measurements to each other. So the acceleration is going to be the derivative of velocity. So acceleration, our acceleration function, we'll call it a, is the derivative of v. So that's going to be negative 6t minus 5. And so the acceleration at t equals 3 would be negative 6 times 3 minus 5, which is negative 18 minus 5, or negative 23. And the units here are going to be meters per second squared. Letter D says, when is the acceleration negative 20 meters per second squared? So we're going to set our acceleration function that we found in part C, this one over here, and set it equal to negative 20. So when is negative 20 equal to negative 6t minus 5? So this is just a real basic linear equation we can solve. We're going to add 5 to both sides. And then divide both sides by negative 6. So we got negative 15 over negative 6. Yeah, I guess I'm just going to leave it like that. We can reduce that, right? Both of those are divisible by 3. So it's going to be 5/3. So yeah, at 5/3, or approximately 1.6, or I guess we could go ahead and call it 1.6 repeating seconds. And that about wraps it up for tonight's homework. Thanks for watching, and I'll see you next time.